Okay, so let's make sure the microphone is open. It is open. Let's get started with the classification of particles. Before we start, I want to tell you that there is that playlist we're doing which is to finish the AS Physics International AQA syllabus as soon as possible. These videos will be also useful for the normal AQA, and I think it might be useful for OCR and Excel, and somehow CAIE as well. But of course, it's gonna be useful for AQA, inshallah. And tell me in the comments if it was useful for you. So, starting with the classification of particles. Basically, we can classify all types of particles according to their spin. Spin is a characteristic property of elemental particles, just as charge is. So we have fermions and bosons. Fermions have half integer spin, for example, multiple of half, and can be an elementary or composite particle. Composite particles are basically made of number of elementary particles, and all known fermions are direct fermions. That is, for every particle there is a distinct antiparticle, which is a particle with certain opposite properties such as charge. Fermions are the basic building blocks of matter. They make up protons and neutrons and include electrons, which together is the composition of atoms. 12 types of fermions, ignoring antiparticles, 6 quarks, and 6 leptons. For the bosons, they have integer spin. And the fundamental forces of nature, like electromagnetism, strong and weak interaction, and gravitation, are called gauge bosons. We've talked about them in details last video if you want to go check it. And they can be an elementary or composite particle. Composite particles are made of numbers of elementary particles. So as we see over here, we have either matter and antimatter, which are made of quarks or leptons. The quarks are classed as fermions and have half integer spin, which combine from hadrons. So it's either they have 3 quarks form the hadron group, so they form baryons, which are classed as fermions and still have half integer spin and include protons, neutrons, and their antiparticles. While if the quark has a quark-antiquark pair, forms the hadron group, so has mesons, which classed as bosons. Integer spin includes the cation and the pion, mediator of the strong nuclear force, and we talked about that mediator also in the last video. Leptons, classed as fermion, have integer spin. There are 6 leptons, 3 negatively charged leptons, each with their own associated uncharged neutrons. Okay. Elementary particles. The elementary particles are fundamental particles that have no internal structure. They are the building blocks of everything, just as we think of elements as building blocks of molecules. Elementary particles can be separated into either bosons or mesons, depending upon their spin. As we saw above, mesons have half integer spin, while bosons have whole integer spin. Integer or integer? Tell me in the comments. We can therefore split the elementary particles dependent upon if they are bosons or mesons. So, the fermions, 2 separate types of elemental fermion, the quark, which have 6 types and 6 corresponding antiparticles, and the leptons, which have 6 types and 6 corresponding antiparticles. For the bosons, 1 type of elemental boson, and there are 6 elemental bosons, and they are just referred to as bosons. The fundamental forces of nature, electromagnetic, strong and weak interaction, and gravitation, and are mediated by a special group of elemental bosons referred to as gauge bosons. The fermions are made up of 6 leptons and 6 quarks and their corresponding particle. What is the lepton? Leptons are fundamental particles with no internal structure. They are not affected by the strong interaction, and they have half integer spin. The leptons' respective antiparticles are the anti-leptons, which are identical except for the fact they carry the opposite electrical charge and opposite lepton number. There are 6 leptons in total. The 3 charged leptons are called electron-like leptons, while the neutral leptons are called neutrinos. The leptons have some characteristic properties. Basically, the particle electron has symbol E and charge -1, mass 1, lepton number +1, lepton electron number +1, lepton muon number O, lepton tau number O. Electron neutrino, symbol VE, charge is 0, mass is near 0, lepton +1, electron number also positive 1, muon number 0 and 0. Muon symbol is as you see, negative 1, 207, positive 1, O, positive 1, O. Muon neutrino, as you see, also O near 0, positive 1, O, plus 1, O. Tau symbol as you see, negative 1, 3, 500, positive 1, O, O, 1. Tau neutrino, as you see the symbol, O near 0, O, 1, O, O, 1. Note that all neutrinos have no charge, and all other are leptons that have charge of either negative 1 relative to, have negative 1 relative to the electron. Although a table of lepton number will be given in the exam, remember that all leptons have a lepton number of positive 1, and all antileptons have lepton number of negative 1. Electron and the electron neutrino have an electron lepton number of positive 1, while their antiparticle counterparts have an electron number of negative 1. This also applies in same way the muon and TO lepton number. Okay, what about the quarks? The quarks are the building blocks of all hadrons, composite particles, ones made out of a combination of fundamental, and they have half integer spin. Quarks can never be found by themselves due to color confinement based upon another characteristic property, which is the color. The quarks have some characteristic properties. Up U, antiparticle U with a dash, charge positive 2 over 3, mass 1.5 to 3.3, baryon number 1 over 3, strangeness 0. Down D, antiparticle D with a dash, charge negative 1 over 3, mass 3.4 to 6.0, as you see it's the one after, baryon 1 over 3 as well, strangeness 0. Charm C, antiparticle C with a dash, have 2 over 3 as well, 1160 to 7,000 to 1440, 130 and 0. Strange S dash, negative 130, 70 to 130, 1 over 3, negative 1 or positive 1 for S dash. Top T dash to 3, this number 1 over 3 O. Bottom B dash, negative 1 over 3, this number 1 over 3 O. All of the associated antiquarks have opposite charge, baryon number and strangeness. Up and down quarks have the lowest masses, and the other quarks rapidly change into up and down quarks. Note that only up and down strange quark characteristics are needed for the exam. Up, down, and strange. Okay? For the next part, bosons. Mediator particles, ones that are exchange particles for the fundamental force of nature, are called gauge bosons. Bosons and some characteristic properties. The photon has the simple and antiparticle self with charge O. Interaction mediated electromagnetic existence is confirmed. All existence is confirmed except for the Higgs bosons, it's unconfirmed, and the graviton is also unconfirmed. W boson has W negative 1 over 3, negative 1, W positive plus 1, weak interaction. Z boson also has weak interaction, but charge is 0, and the antiparticle is self with simple Z. Higgs has HO, self O, none. Gluon G, self O, strong interaction, and graviton G, self O, gravitation. Note that only boson to have an antiparticle is the W boson. Okay. What we go after and cover are the composite particles. Composite particles that are made out of other elemental particles bound together. Protons and neutrons are composite particles, as are atoms and even molecules. The hadrons are strong interacting composite particles. Hadrons are either composite fermions, which have integer spin, these are called baryons, and composite bosons, integer spin, that are called mesons. All known hadrons are composed of quarks and antiquarks. The baryons, which are the fermions, baryons have half integer spin. They are made up of 3 quarks held together by the strong force. Antibaryons are made up of the antiparticle partner of the respective quark in the normal baryon. As every quark has a baryon number of 1 over 3, any baryon has a baryon number of positive 1. As a baryon is made up of 3 quarks, likewise an antiquark has a baryon of negative 1 over 3. Therefore, an antibaryon has a baryon number of negative 1 as made up of 3 antiquarks: proton, neutron, and antiproton. A proton has 2 up quarks and a down quark shown by the UUD. A neutron shows the UDD and has 2 down quarks and an up quark. The antiproton has 2 anti-up quarks and 1 anti-down quark. Has 2 anti-up, so it should be UU with one anti down. Okay, the proton is the only stable baryon. Even a free neutron outside the nucleus decays into a proton, releasing an electron and an electron antineutrino as in beta negative. Quarks and beta decay. In the exam, you may be expected to present beta negative or beta positive with regard to quark charge opposed to baryon change. As stated before, beta negative is a neutron decaying into a proton with the emission of an electron and an anti-electron neutrino. In this decay, a down quark is turning into an up quark, which changes the quark composition from UDD for a neutron to UUD for a proton. This change in quark composition can be represented in the Feynman diagram to the right. Feynman diagrams will have a separate video. It's alright if you do not understand it now, it wasn't explained. Beta positive decay is a proton decaying into a neutron emitting a positron and electron neutrino. In this decay, an up quark changes into a down quark. This changes the quark composition from UUD a proton to UDD a neutron. This change in quark composition and can be represented in the Feynman diagram to the left. Okay, if you're thinking what is the evidence for three quark model? The first evidence for the three quark model, which is three quarks being combined to make a normal composite fermion, was in the Stanford linear accelerator. The electrons collide at high speed with protons. Results showed that the electrons were scattered by 3 scattering centers in each atom. What about the baryon octet, which is the 8-fold way? The family of baryons with half spin composed of the up, down, and strange quarks can be represented in an octet. That this symbol and this simple particles differ only in energy. Okay, what about the mesons, which are also the bosons? Mesons have integer spin and are therefore bosons. They are made up of more than one elemental particle and therefore composite bosons. Mesons are made up of one quark and one antiquark. Family of mesons with spin equals 0 can be represented in a nonet seen to the right. The K series of mesons are known as kaons. The bi of series are known as the pions. Notice that there are 3 uncharged mesons. For the exam, the pion and cation composition is needed to be known. What about the conservation rules? Conservation rules will be covered inshallah in the next video. We'll be talking about conservation of energy, of charge, lepton numbers, strangeness, baryon number, and then we will be going into the quantum phenomena. If you'd like to screenshot and study it before the video, here you go. It's also found freely on the PMT website. It's a PDF. Just go into you go first here, you click physics for the revision part, and then you click the board you want. We do international AQA, right? So here it was unit 1, we're doing currently unit 1. Go down, you choose revision notes, and that was the PDF we were explaining from. You also have definitions. Also, I do like say it's really good to study from another AQA. For example, we were doing particle and radiation. You come over here, you also find key points, you find detailed notes, and you find definitions. The key points are very useful in most cases. So I do agree that you must check it. This, for example, are some key points in the, not flashcards, but in cards. So yeah. Study as much as you can, watch the videos you feel it's useful, write notes if that's what you make you feel good, etc. But make sure to study well. So let's get back to the page we were, and that's it for this video. Have a nice beautiful day.